We will move on to our next theme, gaming to promote health. So like you all know, there are motivated people, for example, like our director, who cannot stop exercising, and people like me who knows the importance of exercise, but still needs some motivation or like fun way to distract me to know that like I'm working out, but I'm not feeling like I'm doing a vigorous workout. There is a growing body of evidence showing that video games can be used to promote health. However, mainstream games have slowly and steadily focused on very fine motor controls while not capitalizing on the opportunity to use video game as a vehicle for gross body movement. So in the next two projects, you're going to see our homegrown adapted active video gaming controllers, which make the entire human body as the game controller. And also you will learn about our specialized exercise device that seamlessly integrates with the virtual environment. You will see how the virtual environment is used to facilitate stroke rehabilitation. Brief introduction to our panelist. Mr. Sam Misko has more than 12 years of electrical engineering and project management experience with a specialization in the development of embedded systems, instrumentation, measurements, and all aspects of electromechanical system design. Mr. Misko is a research engineering manager at UAB's Engineering and Innovative Technology Development Group and a program coordinator of the Autonomous Vehicle Mobility Innovation Program. Dr. Kristen John Mendonca is a postdoctoral scholar for RERCREC. In 2021, he received his doctoral degree in Health and Rehabilitation Sciences from Drexel University. His current work focuses on increasing exercise opportunities for people with disabilities. Dr. Mendonca is also a certified strength and conditioning specialist and an adapted athlete competing in wheelchair football and basketball. Next we have is Dr. Laurie Malone. She's a researcher for the UAB Lakeshore Research Collaborative, serving as an active member of the RERCREC team for the past 9 years. Dr. Malone's research utilizes a multidisciplinary approach to examine the impact of physical activity and sport on the lives of persons with disability across the lifespan. Her recent work has focused on active video gaming as an engaging and enjoyable option for exercise. Recognized for her work in the field, Dr. Malone is a fellow for the American College of Sports Medicine and the International Federation of Adapted Physical Activity. Our next panelist is Mr. Lloyd Cooper. Mr. Lloyd Cooper is the principal designer of Push Product Design LLC, a research and development consultancy for clients ranging from Medtronic to Yamaha. He has an industrial design and mechanical engineering background and directs a team that focuses and executes towards the key design criteria for the RERCREC's Advanced Virtual Exercise Environment Device project, which you'll hear shortly. Last but not the least one is Dr. David Brown. He's a senior vice president and dean of School of Health Professions at the University of Texas Medical Branch. He is also a professor in the Department of Nutrition, Metabolism, and Rehabilitation Sciences and Department of Physical Therapy. Dr. Brown has conducted research at several universities in the study of neural control and biomechanics of locomotion. He has examined motor control issues associated with ambulation after stroke to propose theories surrounding a better understanding of how the damaged nervous system post-stroke reorganizes to create functional locomotor behavior. We can get started with the session. Mr. Misko, over to you. Okay, I think this is the overview of the presentation. We have a video to give you an idea about this project. We'll get started with that.
The Active Video Gaming Study features an adapted gaming board called the Game Plank. This system provides new opportunities for players with mobility impairments to engage in physical activity by utilizing their bodies as the gameplay controller. The Game Plank connects to the Microsoft Adaptive Controller, along with a variety of external buttons, to facilitate active gameplay for individuals with varying ability. First, the game plank must be calibrated by prompting the individual to lean in 4 directions before gameplay. During gameplay, a tablet connected to the system allows for real-time adjustment of factors such as the sensitivity and responsiveness of player game input. The game plank was designed to be adaptable so individuals can play sitting in their wheelchair, seated on a chair, or even standing. Individuals of all abilities can use the Game Plank system to play any video game available on PC or Xbox. Overall, this system provides a fun and engaging option for physical activity. The Adapted Touchpads is another system being tested in the AVG study. It is a series of large touchpads, each mounted on its own adjustable stand, which connects to a circuit board that is recognized as a video game controller. These pads are made with low-cost materials and are designed to be touched, slapped, or even bumped. The stands allow the pads to be placed at varying distances and heights relative to the player. The layout of the buttons encourages physical activity through gameplay. Participants can also play sitting in their wheelchair, seated on a chair, or even standing. Similar to the Game Plank, this system can control most PC video games as well. These 2 devices are great examples of the development and research work being conducted right now in the RECTech labs.
Over to you, Mr. Misko. Sorry, we are just moving him from the attendee to the presenter. Sorry.
All right.
You're good to go.
There we go. All right. Can everyone hear me all right? I think that's a yes.
Yes, we can hear you. Yeah.
Okay. All right, wonderful. Thank you, everyone. We'll go ahead and go to the next slide. So what we're talking about today is the proof of product project we started up, which is a follow-on from RECTech 3 on the balance board device. So we're going to jump right into it here, and then you'll see more about what the device looks like and things like that in the next couple slides. But the first part of the product kind of proof stage was to do market discovery. And in market discovery, we started off initially thinking that a good market for this device, and just really quickly to put an idea in your mind, is the Wii Fit balance board. So we made a bigger, kind of better one that's more inclusive and allows for people not only to have more range of motion on there, but also to get a wheelchair on there or a chair. But one of the initial marketplaces we thought we'd get a lot of traction in was the physical therapy clinics. So we followed an I-Core process where you go out and you do a lot of in-person interviews. You try to establish what your value proposition is to these customers. You identify the end users, things like that. And most importantly, you also need to have an understanding of the revenue streams that would drive the commercialization of a product. We started off in physical therapy clinics, like I said. The use case there being mainly for gamification of the physical therapy regimen. So how could it be adapted into their processes? We did a lot of interviews with them, and ultimately it just looked like the clinics were really kind of cash strapped due to falling reimbursement rates. They were having money, just keeping the doors and lights on with the reimbursement rates they had. So there wasn't a huge interest by that customer in purchasing these products, and I think that was the main reason for we moved on to the next segment. So the next market segment we looked at was inpatient rehab and retirement homes. So in that environment, we had a lot of interest from customers. There's definitely money set aside for recreation and purchase of equipments in these environments. But ultimately, what kind of ended up pushing us out of this market segment initially here was the end user, right? So in a lot of these cases, you're talking about people who are older than 50 years old, so hadn't had a lot of experience in video games and didn't appear to have a lot of interest in the types of video games that we would typically play in a game console or on a PC that could be easily kind of gamified, right? So most of the games we saw people playing at that level were, solitaire or say world building games. So like Sim City, things like that were some of the things we heard. And so those weren't really it wasn't a strong response we got. We did like it from what we heard from the inpatient rehab people and the retirement home directors, but ultimately the end users didn't appear to be very much bought into the idea. So the third segment that we ultimately ended up in here is the universal game accessory market. So this is the big one, right? Everybody's buying their kids the latest game accessories. So if you, at the very bottom of the slide there, you see that it's a price-driven market and it operates largely on the holiday sales cycle, right? So parents and grandparents are buying the kids, grandkids, the next cool game accessory for their device of choice. And this one fits in really well in that segment because ultimately we're trying to get the price down. But there is a challenge, which you see on the second bullet on the bottom left here of the slide, which is the path to market is a little more difficult in this scenario. We can't do your traditional make a sale and then build a product and then ship it. With a higher cost per unit, which you could see in those first two markets. This one is strongly price driven. You need to be under $200-300. And you can do direct to consumer sales, but you need to have a lot of product on hand to be able to ship quickly. If we look at other companies that have recently emerged in this space, 3D Rudder is a product that I'll talk about a little bit later on. They needed about 1.5 million in seed funding just to get off the ground floor and start shipping product. So next slide. So just to kind of talk more about the product before we end the presentation again with comments on commercialization. After we did our market study, we kind of had a little bit more traction about who we were designing for. While we were doing that, we were doing early design iterations. So here you see on the top, the Wii Fit, which is kind of a starting point. On the top right, you see where we ended RERCTech 3, which was the proof of prototype here. And so there we took the guts out of the Wii Fit board and we stuck them into a more robust frame, which could support people on wheelchairs of all different capacities, weight capacity, range of movement, things like that. So the main things we implemented there was adding sensitivity adjustment and bias adjustment and a jump button so that you could still use the Wii board's basic features. It only worked on the Wii video game, but you could adjust sensitivity and bias and jumping and things like that from that little user interface that you can kind of see on the top right that was attached to the balance board. What we wanted to do was take it from there to the proof of product, and that was RERCTech 4 here. The main goal here, right, was to design it for manufacturing, radically reduce the weight. As you can see, that prototype used a lot of aluminum, was very heavy, kind of expensive to manufacture, and also we wanted to have universal compatibility with all the different gaming consoles and PCs out there. So for that, we kind of launched the project with a couple of senior design teams from both the biomedical engineering, electrical engineering, as well as some members from the business school. And with all of those students together, we were able to get going quickly on some brainstorming, ideation, and design. And we used an industrial design consultant, Sean Simmons, from Objective Design. And he was able to help us throughout the project refine our designs for manufacturing and also make some of our stuff look a little bit better. Next slide. All right, so getting into the design iterations, so the senior design team, where they kind of ended up from the biomedical was on your top left picture here, where they created a wooden prototype just to see how everything would line up, and it kind of forced them, as most senior design teams, they went out and worked through all the different problems of how are you going to make handrails and platforms and make it expandable. You can see the built-in ramps, all these different little features that were ultimately realized through that wooden prototype. And it's always good, get something your hands on in the lab so you can start to see where you're doing well or where you can improve. I'm going to move from the top left here, kind of across the top row. The next thing you see is the load cells and how those were built into some feet. And then on to the right, top right, you see kind of the FEA modeling we're doing to start to understand how many load cells do you need to support the weight of different people, different wheelchairs, different assistive devices, things like that. And that really drove what was required for material and manufacturing methods. So as we kind of go down the slide here on the right, you see some different ideas on how to shrink the size and the weight of the board, what kind of materials could be used. We kind of end on this black platform, this very basic prototype on the near the bottom right. And you see these little cutouts for the load cells. We got 5 load cells in this prototype. And I bring your attention to this because this represents our first realization that we could use a composite approach to building out the platform. And so this is basically carbon fiber on either side of a foam core. And that allows the price to go down and your manufacturing methods to be much more simple, right? It's because you can kind of crank these out and stamp them out as you need them. On the left, you see some different iterations. We don't spend any time on the electronics here, but on the bottom left picture, you see a snapshot of our early development of an app. So we moved from what was kind of a tangible user interface in our previous prototype where we had buttons and knobs to putting everything on a tablet so that we could use an interface that's familiar to everybody, which is a touch screen. And with that, you can, have maximum flexibility as far as changing the user interface and adding things or taking away things, redirecting the user to the areas that are most of interest at that particular point in the adjustment. But it allows for real-time adjustment of sensitivity, thresholds, biasing, and we see that in the next slide as well. But the main thing here was that we started iterating the platform design pretty heavily. And then the electronics design, again, we wanted to make it compatible to all different types of gaming consoles or platforms or PCs. Pick out an embedded processor, and then how we're handling all the load cell measurements. Next slide. So in just a kind of a snapshot of where we've ultimately gotten here is the platform. On the platform design side, like I said, we used a carbon fiber based approach. We got away from carbon fiber because it was too expensive. We're using fiberglass now in our composite panels. You can see the new geometries that we're using. So we have a built-in rim around 3 sides of the board, which serves as a barrier if you're on a wheelchair, so you aren't rolling off. And also, that also gives you a tactile feedback. So if you put on a VR headset, you can feel with your feet kind of where you are on the platform. So if you're standing up and you have a VR headset on, you'll know if you're about to step off the platform. Now the back of the board does not have a rim because we've kind of built in a tapered edge there to allow for a wheelchair to roll right onto the board. And then we have load cells integrated in this. We actually have 6 of them, and we moved to a lower cost load cell here, which were easier to purchase in bulk and give us some pretty decent performance. After a couple of iterations, we have arrived at a fairly robust electronic stack, and we've added the LED matrix on top. And the LED matrix basically allows us to give the user feedback in real time about the performance of the board, and it also gives them indicators on how they need to interact with the board more, whether it be in a calibration mode, or if they need to get off the board, things like that. These are all things that were built into the Wii's gaming system, right? So when you had the Wii gaming system in our first iteration, all the games were built for the balance board, all the calibration was built for the balance board, and it was all there in the Wii. So what we had to do was create our own kind of interface here that would always be up and always be in real time and be very responsive for anybody with or without the app loaded up. So this is a separate little LED matrix board that sits there. It's where you plug in the board to read in the signals from the board and send that out to a PC. So it's kind of the central electronic stack that would need to be purchased with the board. All right, and yeah, so we'll go ahead and do the next slide. All right. So with our final kind of prototype now that has been through a lot of iterations, and I can't say enough about our engineering team, starting from students and moving all the way up to using some of our more seasoned electrical engineers here in the last year to try and get this thing to its final state. We're getting closer and closer now to where we think we could start to commercialize this. So this slide is all about kind of that final closing argument on the commercialization outlook. Ultimately, this was a proof of product project. So this is where ultimately we need to end and commercialize. So the first thing I want to mention is the gaming accessory market. So it's one that's rapidly growing. I think we're all aware of the pervasive theme of gaming in our environment, in our culture. No surprise, I think, to anyone to see the chart on our top right here, which shows that remarkable growth that even as recent as this year. But mostly the things I want to kind of give you as a takeaway is the price to enter that market is very, very low, right? As far as to motivate people to buy this, it needs to be on that $200 to $300 mark. It's way below what you would consider for other competitive VR accessories. So if we consider ourselves like purely like a VR accessory, we're way below what else is out there, except for the 3D rudder. So the 3D rudder ships for, I think it's around $150. Now that one, as you can see, is made to be used when you're sitting and requires a lot of fine control of the board. So you're basically making that board tilt with your feet. And it's not a natural movement, I would say. It's kind of a learned movement and requires some really fine motor control of your lower limbs. On the right, you see the other thing that's out there for VR. That's an omnidirectional treadmill. This is one of the cheaper ones, and even that one I think is $1,000 or $2,000 a piece. So you can go up to, I think close to $10,000 for the nicer omnidirectional treadmills. So this is kind of a space where we think we could do pretty well as a VR accessory, and especially if we can get under that $200 or $300 mark, which with our latest estimates, we think we're very, very close to. We'd obviously have to partner with somebody who has supply chain understanding and move forward with the manufacturer to get exact estimates on what the price to manufacture it is. But I think we're very, very close now to reaching that threshold of around $300. The large investment that still needs to be acquired is probably on the order of $1 to $2 million. And again, it is based on what we've seen other companies require to launch a product such as this, the 3D rudder, which you see a picture of here. They've had a couple extra rounds of funding after that. They partnered with PlayStation to get better market penetration and get better marketing. So they really are a bit of an example of how a gaming accessory can exist on its own from a third-party company with direct-to-consumer sales largely. So we're using them as kind of a template for right now and understanding how we could make it into the marketplace on our own as a gaming accessory. And I've already talked about the holiday sales cycle, but that's kind of where we've ended our efforts right now, is that we do have to go out and look for this investment, probably from a private investor. We are looking at SBIRs and other funding mechanisms like that, but it's going to be a tough one because ultimately this one is got to stand on its own pretty quickly and be able to launch pretty rapidly. So it does require you have a large amount of stock built up on hand so you can ship quickly. And with that, I will pass on the presentation out to some of our other researchers who have had more hands-on with their own research on gamification, and also using our game plank, as we call it, to try and understand usability and other factors associated with this.
Hello, everyone. My name is Kristen, and I'm excited to talk to you about how the touchpads were developed for the usability study. Next, please. So this work started back during my doctoral studies, where I wanted to pursue a quick and easy way that we could substitute sedentary video game controls with large movements, therefore creating active video games out of the titles that we wanted, and to use the movements that we wanted as well. And so I really had this idea of optimizing the end user control, such as being able to use many different video games with the same device, able to use different video game devices, and then also being able to adapt to many different users and adapt to even different goals. So my background is in exercise physiology, but I also have a long history of health coaching and strength and conditioning. So I kind of thought of this as a way to start to design exercise programs with video games, rather than just having a simple device that played one or maybe two different games. However, as I started to explore this, I didn't have a good grasp of what movements would actually be best. If we could do anything, what should we use? And then also, if we replaced the hand controls of a sedentary video game, would it diminish the experience for the player in a few different aspects? Next slide, please. So what are they? The touchpads are simply just a large target that's placed somewhere around the player. And what it does is it makes them reach and to make contact with this target. And every time they do, it triggers a video game command. This contact can either be by some of their skin, or it can be by touching one of these targets with a conductive material, such as aluminum tape that we use here. The strategic layout is really where this system is versatile, because we can move the buttons up or down, left and right, and change their orientation to the player. The targets need to be large because we also want to optimize the participants' focus on the game, meaning that we don't want them to have to look away from the screen while they're playing in order to find where the button is. All of these touchpads are wired into a simple device called the Makey Makey, which is a STEM tool to teach kids how to learn about science and technology. But interestingly, it gets recognized by the computer as a video game controller, meaning that we can connect these jump pads with a simple wire, and they will be recognized by any PC as a video game controller. Next, please. So my preliminary work consisted of two different studies, one small, one a little bit more involved and larger. The first study taught me that there needed to be some refinement in these early prototypes that I was putting together, mainly that the buttons were breaking or becoming disconnected due to people reaching out and hitting them pretty hard. And so I realized I had to make them more robust, and they were also a bit too small. So even though I wanted the player to be able to focus on the screen the whole time, the buttons were still a little bit too small. So when they reached out, they had to actually look for them, which was introducing some frustration. The second prototype was refined to make the buttons much larger and more robust so that the player could hit them as they wanted to. And we had really good results. Exercise intensity was really good. However, there are only a few participants in the study that had a mobility limitation. Next slide, please. So here's an example of the work I did for my dissertation. There were only 4 inputs, so 4 different touchpads used, and they were playing one game where they were able to move up, down, left, and right. Next slide. I was excited to transition here to the UAB Lakeshore Research Collaborative to get a chance to refine the prototype into something that could be used with individuals of a wide variety of ability, especially those with movement limitations. So I started to work over the summer on a new version of these touchpads that would be able to be played by someone who is either standing or sitting in a chair, or maybe their wheelchair, or even standing with their mobility aids. So this low fidelity prototype, we wanted also to make sure that it could play a handful of different games, unlike my previous work, which focused on the comparison of one game. We also increased the number of touchpads from 4 to 6 to allow for a different range of video games to be used. Next slide. The construction of the touchpads themselves is very simple, and it uses low-cost materials. It's a particle board in which you can see alternating strips of aluminum tape, which is highly conductive. And if you look at the picture on the top view, you'll see that the strips don't go all the way to one side of the board, and that's intentional. If you look at the rear view, each strip connects around either the left or the right side of the board. And then we simply just align a group wire on both sides. One wire is attached to the ground. The other side is attached to the appropriate video game input. While it looks odd at first, what this allows for is the player to not be tethered by any wires. So this has been attempted before using the same device, but in all of the other iterations, the person had to have a wire taped to them, or they had to be grounded in some way. This allowed the player to be free to move as they wanted to, and they're instantly grounded and provide an input just by touching the pad at once. Next slide, please. So here's a side view. Not all of the inputs are shown for visual clarity, but as you can see, the person is playing the game from their mobility device, and they're also on a slight platform with a ramp. This allows for some parallel bars to be there in case they want to lean against the parallel bars as well. You'll see that the button for down and up, two of the inputs that we used, are in front and behind the player. These are wired to the controller, which is set onto the ground so that it doesn't interrupt their visual field. That is connected to the PC. And then finally, the PC is projecting the game onto a nice large screen, so they have a clear line of sight to the game. It's easy to see, and it's easy to hear all of the information as well. Next slide, please. Here I provide a top-down view so you can get an idea of how all of the inputs, all 6 of them, are placed in relation to the player. So here we have a standing player who's inside the same platform with the parallel bars, and you can see that the buttons are all placed around them. However, they are a little bit out of reach. When the player starts, we move them in accordingly, and we try to adapt them as best we can so that the player has to move in order to play the game. However, it's not frustrating. We want them to be able to have success consistently as the game goes on. And we also want to account for a little bit of fatigue as well. What you'll also notice about this setup is that it has a clear lane of egress, meaning that the player, no matter if they're in a wheelchair, using a mobility device, canes or crutches such as I do, they have a clear lane to get into the setup and to get back out. You can see there's a little bit of clutter of wires, but it's all placed in front of the player, and the player doesn't have to be concerned with getting caught in any wires or any fall risks due to that. Finally, once the player is in, we just take the down button and we just slide it in behind them so that they can reach back to hit the down button, and we can easily slide it back out of their way when they're done playing. Sorry, took a second there. All right, thank you very much. I'm gonna hand it over to Dr. Malone, who's going to talk about the results of the usability study so far. Thanks.
Hello, everyone. I'm excited to be here after all the great work you've been hearing about this morning. And particularly, next slide, please. So particularly, as you have heard from Sam and Kristen, tremendous growth has occurred with our AVG work since the last RECTech cycle. From that work, we published 4 peer-reviewed journal articles and currently have a scoping paper under review. And most excitedly, the development of the 2 new active video gaming controllers. Next slide, please. So following from the development work, the 2 gaming controllers are now in the RECTech lab, in the RECTech research lab. Extensive testing with various games and accessories has been done, along with preliminary usability testing with staff. As of last week, we began recruiting participants with mobility impairments for usability testing, and as of today have completed data collection with 8 people. The sample includes individuals with stroke, spinal cord injury, and amputation. Based on functional ability and comfort level, each individual chooses to either play seated in their own wheelchair, in a four-legged chair, or standing. Next. So each session is taking about 2 hours. So, sorry, 1 second. My computer was, so the usability sessions are each taking about 2 hours. We have the players each play a total of 9 games, 5 minutes each, split amongst the 2 gaming controllers, the game plank and the touchpads. The controller and game playing order are randomized. A series of measures are collected during the sessions. RPE and enjoyment are collected after each game. Self-efficacy before watching a demo video for each system, and then after completing gameplay on that system. And then they answer 2 usability surveys after gameplay on each system. And then finally, at the end of the session, a feedback questionnaire. Next slide, please. So here are some photos showing gameplay on the game plank, where we see on the left somebody seated playing in a wheelchair, and then in the middle sitting in chairs, and then on the left playing seated or standing. Next slide, please. And here we see gameplay using the touchpads. So again, on the left, somebody seated in their wheelchair, in the middle there, in a four-legged chair, and then on the right, playing standing. Next slide, please. So here, we'll start talking about some of the data we've collected thus far. So starting with RPE, we see that average RPE data, rating of perceived exertion, has shown moderate intensity exercise for both controllers. Next slide. For enjoyment, using a visual analog scale from not at all enjoyable to extremely enjoyable, participants have reported moderate to above average levels of enjoyment for each game on both systems. Next slide. When participants are asked about their certainty in completing different gameplay tasks for each system before and after gameplay, so far we have seen a slight increase in their self-efficacy using the game plank, whereas a slight decrease has been found with the touchpads. Next slide, please. So using the standard scoring methods for each usability survey, participants have reported above average usability for both the game plank and the touchpads. They're asked questions such as, I think the adapted gaming board would provide a physical activity option for persons with mobility impairments, or using the adapted touchpads enables me to be more active when playing video games. Next slide, please. Here we see some comments made by the participants thus far. For example, something new to keep alert and enjoy. It was cool to watch my character turn as I leaned left or right. Entertaining, etc. All right, on to the next slide, please. So next steps, we will complete the usability testing. We're hoping with another 20 participants, and then we'll refine both of the AVG systems. Considerations from our testing thus far will include gameplay mode, previous gaming experience, and game selection and player preferences. As we develop the intervention, we will design a program that includes an integration of the newly developed controllers, as well as some of off-the-shelf gaming systems. We will assess various exercise and psychosocial outcomes, along with related secondary conditions. We will also explore single versus multiplayer options. Overall, we aim to develop an accessible, active, and an enjoyable exercise opportunity for all. Next slide. So in summary, we have seen the successful development of 2 adapted gaming controllers. Participants can play seated, standing, and/or with mobility aids. Preliminary data suggests moderate to high enjoyment, moderate intensity exercise, and above average usability. Next, we will refine the controllers, implement an exercise intervention, and disseminate results. I'd like to acknowledge our other AVG team members for their contributions. Thank you.
Thank you, Laurie and Kristen. Over to Mr. Cooper.
Thank you, Sonia. I'm going to briefly touch on a number of areas and then try to leave as much time as possible for Dr. Brown to focus on our latest research. So I want to provide an overview of the AVID development along the continuum towards full commercialization, and particularly focus on this latest phase from RERCTech 3 to 4. I want to show a 2-minute video summary of the device in use in the Lakeshore Lab. And then I want to talk about patent and tech transfer and our kind of commercial development plan for future direction, and then turn it over to Dr. Brown. So next slide, please. So AVID has gone through a very extensive development effort, from beginning with criteria definition, going through concept development, concept refinement, and into design for production. And next slide. And this is the broad area that we've been focusing on most recently, where we're transitioning from concept refinement into the first parts of design for production. And the key areas that we've been focusing on most recently have been the development of the control system and reducing the cost and complexity of the system down to a customized printed circuit board and a hub motor configuration, which can be developed at what we believe to be an adequate price point to take this into full-blown production. We've also put a great deal of time and effort into the intellectual property side, because we believe that strong patent protection is going to be essential for a commercial development partner to really take this project on and invest the resources that are going to be required to take it into full production. And as Sam has talked about, this can be a quite daunting process. And so that we want to make sure there's as much security as possible for our strategic partners. In summary, the AVID program has been developed to meet 3 broad criteria. The first criteria is around the ability to interact with existing online content, the virtual integration aspect, which Dr. Rimmer alluded to in his comments. The second broad criteria has been the development of a fully adjustable system that can meet the needs of a wide range of users. So from an individual that may be post-stroke, that can stand and walk up to the system and grasp the 2 hand cranks, all the way to a wheelchair user that has the ability, that may have compromised grip strength, but needs the system to be adjusted down so that they have the ability to provide the most efficient energy input into the system. And then the final criteria has been the development of what we're calling the control system, which is a combination of sensors as well as the energy device, where the individual can actually put energy and exercise into the device, and we can adjust the resistance in a very precise manner. What we can also do that's unique is that we can provide supplemental power to allow an individual that may have an asymmetric strength imbalance to be able to interact with the system with more symmetrical balance and cadence. And so the best way for me to summarize this criteria is to play a 2-minute video now, please.
The Advanced Virtual Exercise Environment Device, or better known as AVID, is a device that allows users to exercise both arms and legs. Unlike devices with mechanical analog linkages, AVID allows the user to provide rotary input for each limb into an electronically controlled hub. A key benefit is that a user can exercise both arms at an equal effort, even when one arm is weaker than the other. This is accomplished by a unique control system that precisely monitors energy input into each axis. Based on the input of one axis, Carefully regulated power or resistance can be applied to an adjacent axis based on the goal of the exercise. This control system can be set to engage automatically or manually. As an automated example for post-stroke recovery, a user with a stronger right arm could begin to crank the device. This force input provides supplemental power to the weaker arm to assist the user in keeping both arms cranking at the same cadence. As the user gains strength on their weaker side, the system can automatically shift from asymmetric to more symmetric loading. As a manual example, Avid can also be set up with independent resistance control. Unlike standard arm cranks, where the resistance felt is equal on both sides, Avid allows a user to decide the level of difficulty for each arm. Alternatively, full electronic coupling allows Avid to behave like traditional arm or leg ergometers, as if the crank arms were mechanically connected. The device structure is based on articulating arms that can be electrically adjusted to different heights and relationships. We have also explored pairing the Avid with online exercise platforms. An example of this is called Zwift. This allows people with disabilities to connect with others during exercise sessions without having to travel to a specific destination to engage in a training session. We hope you have enjoyed this presentation on the Avid system.
So what I'd like to focus on for just a moment is kind of a more detailed dive into what we believe is the most compelling part of this technology, which would warrant full commercialization. And so over the past 6 months, we were wrapping up a multi-year effort with our patenting process, which is involved in the 3 areas of criteria that I mentioned, but with specific focus on this unique control system. So I want to explain this with a more simple illustration. So next slide, please. So the video touched on this. One of the potential target markets is post-stroke. And so the challenge with providing exercise to an individual post-stroke, as most of you are aware, is that individuals often have an asymmetric strength and balance. And with conventional exercise equipment for an individual post-stroke, what generally happens is that the weak side of the body is just along for the ride, and the strong side continues to do all the work. And so with this diagram here, what this is showing is that if you were to ask the individual to go up to the device and pedal at a 60 RPM, just very consistent RPM motion, what Avid can do is it can plot, hold the slide for a moment there. What Avid can do is it can plot the change in velocity over time, which you're seeing real data coming off of the Avid system. And the blue line represents the strong side. And so the strong side is at this amplitude of velocity. And when I'm talking about measuring angular velocity, what I'm stating is that not only can the system measure the 60 RPM, it can measure very slight changes in angular velocity as the crank may go over the top and then accelerate down the front end of the crank cycle. And so when the individual attempts to crank the device on their weak side, as you can see, this is very typical. There may be a very low delta between the energy that they're able to impart between their strong and weak side. So Avid can simultaneously measure the change in angular velocity on the weak side, which is represented by the red line. And in real time, it can calculate the delta between those two energy inputs. Next slide. Which is represented by the yellow line. And so in summary, to simplify this, imagine taking the red line of energy and adding on to the yellow energy, which is the delta. And now the individual is able to stand at the device and crank with equal cadence, almost equal cadence on the right and left side with their strong and weak side. We're requiring the individual to put forth as much effort as they possibly can with their weak side, with the addition of the supplemental energy. And so imagine if an individual post-stroke were to train on Avid for a longer period of time. What would happen would be, because their weak side is working as hard as it can, it's gradually becoming stronger. And as it becomes stronger and they were to train on Avid, Avid would automatically observe that delta between strong and weak would diminish. So it would energy appropriately, forcing the user to put forth more energy on the weak side until ideally their sides became balanced. So that's a quick summary of what this functional control system can do. So next slide. So what I'd like to touch on now is the commercialization model and building out these case studies. So next slide. So this is a diagram of essentially the commercialization model plan. And it begins with the domain expertise that's represented by Lakeshore and UAB and individuals like Dr. Brown, you'll hear in a moment. And the idea is to focus on unique areas of distinct research for unique patient populations like post-stroke, to do empirical studies to determine clinical benefit. And then based on these studies, build exercise therapies that provide maximum clinical benefit for these user populations. And by building out these studies, by building out these therapies that we've empirically proven to be clinically beneficial, we believe that's the best way to engage strategic partners and justify the development effort. And these could range from a large number of strategic partners like Zwift that you saw in the video, because all of these partners share the goal that Avid has to reach the largest number of customers possible at the lowest possible cost. And then the second part of this is also a path that Dr. Rimmer talked about in his opening comments, the algorithms. Because Avid has a feedback loop, it monitors the energy input through sensor data and it's recording it. What we also believe is possible is that combined with sensors, wearable sensors like Whoop and the Apple Watch, we can look at physical data, and combined with the actual data of the energy inputs, we can understand how to more effectively optimize our algorithms to design improved exercise therapies. Final slide, please. And so in summary, this is an outline of the ideal strategic partners for this project. So you have Apple as a sensor device with the Apple Watch. You've got Google as a content provider, as an example of digital content, mapping everything from roadways to walking through national parks to art museums. You've got Peloton as a device manufacturer, and Zwift is a gaming device. And so with that, I'd like to pass this on to Dr. Brown to talk about our latest research.
Thank you. First of all, shout out to all my colleagues there at UAB. Cheers from University of Texas Medical Branch in Galveston. Thank you for including me in these presentations. I came to this project as a physical therapist, very interested in providing opportunities for people after they've had their stroke to become fitter, to engage in exercise, all the things that we talked about today. But I have another perspective as well that I'm adding to this project, which is after a person's had a stroke, they need to relearn how to use their brain. The brain is not working the same way it was before the stroke. So by giving people movement opportunities, challenging movement opportunities, people can learn how to control their brain better, how to control their arms and legs better. And I see the Avid as a great opportunity for that learning experience. Next slide, please. So here's something that people need to learn about after they've had their stroke. There is something called interhemispheric interference, and you saw examples of it in the video that you saw earlier. The idea is that after a stroke, not only is there damage to the neural structures of the site at the site of the stroke, but there's also an influence from the non-lesioned cortex. The non-lesioned part of the brain is sending what we call an inhibitory signal to the areas around the site of the stroke. And that is a maladaptive compensatory mechanism used by the brain to try to minimize the use of the lesioned cortex and maximize the use of the non-lesion cortex so that the person can survive in their environment by primarily using their non-paretic arm. So while that may be a good survival strategy, in the long run, people want to be able to use their paretic arm again, use it functionally, and use it on an equal basis with their non-paretic arm. So the great advantage provided by AVID is this simulated split crank type situation where one arm can move independently of the other. And you saw examples of a person pedaling with hemiplegia with their arm where the non-paretic arm was moving kind of quickly and the paretic arm was sort of lagging and moving slowly along with the non-paretic arm. Next slide, please. So the study that we designed was a comparison of two-armed versus one-arm split crank cycling. And the idea is that we asked the question, can a person who is recovering from a stroke, who has had a stroke, can they perform arm cycling with the paretic limb as well as the non-paretic arm? Can they coordinate the two arms? The hypothesis is that no, interhemispheric interference, or IHI, I think I'll just call it from now on, prohibits or interferes with the use of the paretic arm. So if you ask a person to pedal with both arms, the paretic arm will always suffer from the interference of the non-paretic or non-lesioned cortex, preventing it from moving at the same speed. So what we did, and we're still collecting a little more data. We've had 17 completed studies with individuals who have had a stroke, as well as 18 who have not had a stroke, as a comparison of a nervous system that does not have this IHI maladaptation. We have 2 more scheduled. And we had them perform split crank cycling, one where both arms were trying to pedal as hard as they can, which we call the max test, and the other where 2 arms are doing what's called a ramped submax test. We had them pedal slow and then faster and then faster and faster. And then we compared that with the same max test and ramped submax tests with just one arm individually doing the pedaling. So in one case, it would be the non-paretic arm pedaling at its maximum effort. And in the other case, it would be the paretic arm pedaling at its max effort. Next slide, please. And what we saw is something very similar to what you saw Lloyd had presented earlier. If you look at the 2 graphs at the upper right-hand corner of this slide, you see that when a person is trying to pedal as hard as they can with both arms trying to pedal, the paretic arm in the bilateral case is going relatively slow, approximately 8 RPM. But if you ask the paretic arm to perform as fast as it can when it's unilateral, which means that the non-paretic arm is off to the side, not doing anything, you can see it can approach 25 to 30 RPM. So same arm, the paretic arm, but in conditions where the non-paretic arm is involved, it is greatly hampered, disturbed by the involvement of the non-paretic arm. But with the paretic arm unilaterally performing, showing its capability without the non-paretic arm involved, it can do really quite well. And during the ramp test, which is the data underneath that, you can see that as we're asking the person to pedal faster and faster and faster, the orange is what the paretic arm is doing during the bilateral task. And you can see that the paretic arm actually goes slower and slower and slower the more we ask the person to pedal faster and faster and faster. And once again, this is a hallmark of that IHI phenomena, where the harder the non-lesion cortex tries to accomplish this task, the more it interferes with or inhibits the lesion cortex from participating. Next slide, please. So what's the solution? There's a lot of data that suggests, a lot of data done by other researchers as well as myself, that suggests that this IHI phenomena can be overcome if you give people appropriate feedback and appropriate challenge to try to overcome that inhibitory influence of the non-lesion cortex over the contralateral cortex. So as Lloyd described, we want to connect the AVID to a Zwift-like application. And in this case, the idea is that we ask participants post-stroke to basically race against themselves, have their paretic arm race against their non-paretic arm. But the goal here is not to win the race. The goal is to pedal with both arms collaboratively. So the two arms, the two cyclists, one being the paretic arm, one being the non-paretic arm, trying to stay with each other. And this is a more collaborative way of playing the game of Zwift, where the goal is to stay up with your partner, as opposed to compete with them and beat them. So we call that the Rimmer game. I don't know, it just happens to be the same as Dr. Rimmer's name. There was no intention for that to happen. But the idea is that we'll give people an opportunity to practice this over a 6-week period, 2 sessions per week, give them opportunities to try to extinguish that inhibitory control and try to figure out how to get both arms to pedal at a similar rate, starting at very slow RPMs and then progressing up to faster RPMs. And then we'd like to develop some home exercises because 2 days a week, 30-minute sessions will be fun and engaging for them, for the individuals. But we also want people to be able to practice some of these things when they have some spare moments at home. So next slide, I believe. Next. There they are, the noise. There they are trying to keep up with each other. Thank you, Lloyd and Foster, for providing this video. Okay, you can stop the video. Stop the video. So if we're successful with this second phase, the training phase, we'll be able to answer the question whether persons recovering from stroke can extinguish this IHI. So in addition to engaging and having fun during a physical activity, they're learning how to use their brain in a more functionally relevant and functionally important way. And that this could be part of this new product line that Lloyd was describing, where we can partner with Zwift to make this something that they can offer individuals who want to engage in this kind of activity. Thank you very much. Oh, and I should thank my colleagues in collecting the data and running the experiments, Brandon King, Kristen Mendonca, Jacob Davis, and of course, Sangi was always there keeping an eye on us, make sure that we, oh, there's a slide on this. Excellent. Thank you, everybody.
Thank you, Dr. Brown. Thank you, Lloyd. In interest of time, we'll skip the question and answer session now. We will take a short break for lunch and we will start again sharp at 1 p.m. Central Time. Thank you all.